Hi there, my name's Rich and welcome to my Chat Physics Live 2021 presentation, Creative Practicals on a Budget. I've taught high school physics in the UK and abroad for over 10 years now, and in this presentation I want to share with you some of the practicals and demonstrations that I've found to have the biggest impact on students' learning, but also for the lowest possible cost. So why creative practicals on a budget? Well, as I said, in schools that I've worked in, I've found that there are sometimes limited resources for physics teaching, and a good majority of physics equipment usually only gets an outing once or twice a year. It's very expensive, and for the rest of the year it tends to sit on a shelf, or worse, budget reasons, I'm not able to order the equipment for my school. But I still want students to have a hands-on experience for that particular topic of physics. So in this talk, I'm going to share with you some practicals that can be taught with relatively cheap and easily accessible materials that you can either buy in a supermarket, hardware store, or that you can take from your laboratory prep room. Okay? This talk is primarily aimed at PGCE students and NQTs, or recently qualified teachers, but if you've been teaching longer, feel free to stick around. You might find something that you may not have done before, or something that was useful. Right, let's make a start. Practicals are going to be magnifying glasses, making telescopes. For this, you're going to need two sets of magnifying glasses, so converging lenses, and ideally two of them with different focal lengths. The first practical you can do is you can demonstrate how to find the focal length of a lens by getting a sheet of paper up against a wall and a magnifying glass and projecting an image, and where it comes into focus, the distance between the lens and the screen is the focal length. So that's a really good way to sort of visualize focal lengths for students. And you can talk about different sizes of focal lengths with different sizes of magnification. I'm going to be recording the focal lengths of these two, and we're going to be putting them together to make a telescope. So I'll measure the second focal length of the larger piece of the telescope here, and it should come into view there like that. Now it's a little bit hard to see on the screen because it's a bright day when I'm filming. You'll get a better result if you're in a classroom or a room with just one window open and it's quite dark. Okay, here's a better view of the images that you can see over here with this setting over here, this setup. And we're going to look now at having all the equipment together. So I measured the focal length. The first one, the large one, is 21 centimeters in focal length, and the smaller one is 12 centimeters in focal length. If I add the two lengths together, if I want to make a telescope, I have to put those lenses the total focal lengths apart, so 33 centimeters. And the magnifying glass with the shortest focal length will give you the eyepiece. Now, what I normally do is I let the students kind of figure that out for themselves and see what happens if they put the eyepieces round the wrong way, and that gets us to discussion about magnification. Now, optics benches and ray benches are fantastic for this, but it kind of takes you away from it. So what I'm going to do instead is I'm just going to clamp the two lenses with a piece of plasticine on a meter ruler. So I'll just make sure they're 31 centimeters apart on a meter ruler. The plasticine, it will hold even a heavy magnifying glass like I've got here. It will hold it, but you can also take off the lenses as well. I want to use these magnifying glasses for other things, so I'm going to just stick them there like that. Okay. This is also quite good because it means that I can wiggle and adjust the length of the eyepiece in case it's not 100% in focus, if I made a mistake in my measuring. Okay, and so let's go outside and have a look at what this looks like set up. So I'm outside here, and you can see, you have to excuse me, it's quite difficult to film like this, but I'm outside here and you can see that it should have about 2 times magnification because the focal lengths are about twice, the two different focal lengths are about twice the difference in size, and we're able to get some magnification here. This is really great for the kids. The kids love holding it up and photographing it with their phone as well. I find this, even though it feels a little bit sort of rough and ready, it's a much better experience than just using an optics bench. Experiment is resistance with pencil graphite. This is a great experiment that I've adapted from Make Video about 10 years ago. Now you're going to need a multimeter for this. I know I said practicals on a budget, but I highly recommend you make the investment and order, if you don't have any, a set of 10 or so multimeters. They're great for Key Stage 5 physics, Key Stage 4 physics, and if you want to teach electronics or systems and control as well, they're really, really handy. You're also going to need just a pencil graphite, and do make sure it is pencil. You will not believe the number of students that have used colouring pencil for this. It will not work, obviously. And I'm going to start by drawing a rectangle, and I'm going to shade that in. So we're going to speed that up because you don't want to see me colouring in, so let's speed that up. And you need to make sure that it is really, really shiny. You can see here that I'm really making an effort to cover all of the layers. Right, so the first thing we can do is just measure the resistance of this with our multimeter. So I'll set my multimeter, we'll just have to grab it there. We'll set my multimeter to around 20 kiloohms, or the 200 kiloohm range that it measures, and then my readings will be in kiloohms. That means it can measure up to around 200 kiloohms or 20 kiloohms. Okay, this is why you need a multimeter for this. An ammeter and a voltmeter connected won't work for this. Okay, and so what I'm going to do is just use this to measure the how length and resistance vary. So this would be great for key stage 4 or key stage 5, and you can record the changing resistance with length and do an investigation to look at how does length affect the resistance, and then apply this to wires as well. You can even extend this for key stage 5, and I've done it in the past where we've actually worked out using resistivity and looking up the resistivity of pencil graphite, the thickness of the layer of pencil graphite over it. Now what we can do, just going back to a simple form, is we can take a table of results, and as we vary the length of the vary the length and measure the resistance, we can plot a graph of resistance on the y-axis versus length on the x-axis, and we should find that it is directly proportional. So that's the first experiment. Though, to make a variable resistor out of this. So to make a variable resistor, what I'm going to use is a 9-volt battery, but you could use a power supply if you want. And I've got a wire, the black wire there is connected to the negative end of the terminal, and the red wire is connected to the LED. You need to make sure that an LED is connected around the right way. Sometimes students will mix those up. And you can see here that as I'm going to place those two terminals along the graphite, I should create a variable resistor. Now I've just turned the lights off there so we can see it lighting up a little bit clearer. And what we're going to do is we'll just place it on the graphite, and we can see it lights up. As I put the two probes closer to each other, the LED gets brighter, and as I put them further away, the LED will get dimmer. Okay, this is a great experiment that you can do for key stage 3. If you do it with key stage 3, please make sure you don't connect the two terminals together like that. Otherwise, what will happen is if you connect the two crocodile clips together, the LED will burn out because there's 9 volts going across. And a resource I made, and decided to adapt it and use it to investigate resistors in parallel. So I'll share this worksheet with you, but what you've got here is essentially 4 rectangles that we're going to shade in area. We're going to measure the resistance of them, and we'll shade this area together and connect them as we go along. So I'll shade the first area. Let me just speed that up for you. And again, make it really shiny, as shiny as you possibly can. And in this case, I'm going to grab my multimeter, and I'm going to do the exact same thing as before. I'm going to measure the resistance of this resistor that we've created at the furthest possible end and record it in my table of results down below. So we'll just record that now. I'll record our data. There we go. And now what I'm going to do is I'm going to shade in the second area. And so we'll speed that up for you again. Again, make it as shiny as you possibly can. And we'll record the resistance of the second resistor, like so. And we'll record that in our table as well. Now what we could do after this is continue shading the other 2 squares below, but we won't do that now. What I'm going to do is connect the 2 resistors there like that by shading that up there like that. And I'm going to measure the resistance between these 2 resistors that are now connected in parallel and record my measured value in the table below. And what I'm going to do, or what I get the students to do, is actually work out what the resistance should be if of those 2 resistors in parallel. And we can see that the value, we'll just do the calculation there. We can see that the resistance value is about right. We're about a couple of kiloohms off when we get our calculated resistance. And that will lead us into a discussion as well as to why those 2 resistances aren't matching the exact values. There's a big discussion there about obviously how I shaded the graphite. Did I connect it properly? Was there an inaccuracy as I was recording my data? But then This is a great experiment for students to easily visualize what is happening to resistors in parallel. And all it costs is a multimeter and a few sheets of paper. Experiments involves using a measuring cylinder to measure waves and radioactive decay. So we're going to have 3 experiments here. Our first one, we're going to look at standing waves in a measuring cylinder. Okay, so this is a cylinder with some water in it that you can see there. So essentially what we've got is a pipe that is only open at one end. And so for the first harmonic for a pipe only open at one end, the standing wave is going to equal a quarter of the wavelength. So in a second, I'm going to measure a quarter of a wavelength down and fill my water up to the mark line. And I'm going to measure the quarter of a wavelength of a tuning fork at C note. I'm just going to put my microphone here so you're going to be able to hear what happens at this level. Okay, so when I strike the tuning fork at this level, when I place it lower, you can hear that the volume increases as it gets nearer. We've created a standing wave. We can extend this practical as well by looking at the levels of the different harmonics by basically putting a pipe inside of the measuring cylinder and extending the length of the pipe closed at one end. Okay, our second experiment, we're going to go somewhere a little bit darker. We're going to just use a laser pointer and fill our measuring cylinder all the way to the top. And it's a little bit tricky to see here because you need to have it quite dark, but you should be able to create total internal reflection inside of the measuring cylinder. If it's a little bit tricky to show up, you can use a few drops of milk to help the laser show up. It also helps if you are doing this experiment without a cat around as well. So hopefully we'll just move him over there and we'll go on to our last experiment, which is radioactive decay simulated with non-alcoholic beer foam. Okay, there is a great article already, a great presentation on the Chat Physics website that you can check out, and we're going to run you through how to do this experiment in a little bit more detail. So the first thing I'm going to do is I'm going to use non-alcoholic beer. You could use alcoholic beer. If you don't want to use non-alcoholic beer at all, you can use Coca-Cola or any other soda, but it will run a lot quicker. So what we're going to do is we're going to pour it really, really badly so that we have the whole measuring cylinder filled up with nothing but foam. And we are going to start a stopwatch in a second, and every 30 seconds we're going to measure the height of the beer foam. So we'll make a marking at the bottom of the, we'll start the stopwatch now, we'll make a marking at the bottom and the top of the beer foam, and every 30 seconds we're going to record how far it has gone up and how far it's gone down. We're going to record that data, we're going to measure those heights and put it into a table of results that you can see here. And as you can see, what we get is pretty much an exponential decay over time. If we were to extend this a lot longer, over more than 3 minutes that I was recording for, you would get a really, really good exponential decay. It's a really great way for students to visualize the randomness of decay, but also that it is exponential. Well, I hope you found that presentation useful and you found at least one of those practicals useful that you may not have tried before. This is by no means an exhaustive list of all the different practicals you can do on a budget, but they stem from the same core belief that you can take everyday items or lab equipment and use them in a way that they may not necessarily have been intended to be used. That kind of stems or forms a basis of a lot of the philosophy I have about teaching practicals, taking equipment and using it in a different way. I really encourage you to go out and try the same thing. Take some risks, do a practical in a slightly different way, alter it slightly. It may not go well the first time, in fact it may go wrong and you may not use the practical at all, but I guarantee you that if you keep doing it this way, you'll find practicals that you may have never thought of doing in the past, and you can add them regularly to your teaching rotation. Anyway, I hope you liked my presentation for Chat Physics Live 2021. Thank you very much for your time, and I'll speak to you soon.